So for this example, we want to take the GDP dataset and test if that correlation coefficient we got in the previous, R equals, or R is approximately 0.874, is significant using the standard level of significance alpha equals 5%. So the way we're going to start this, right, we don't have that same sort of verification work that we did before. We're going to jump straight into our hypotheses, where here, because we're just seeing if there is significance, we're not trying to determine whether it's positive or negative, we're just looking for any, our possibilities are that rho is equal to 0, which is to say that we don't have any significant correlation, so in our language that's no correlation, or if rho is anything other than 0, where rho being anything other than 0 indicates some significant amount of correlation between our two datasets, between a country's GDP and their CO2 emissions, where because that has an equality, that's our null, and our alternative is that there is some correlation. So be careful here, rho equals 0 means that there is not any correlation. Rho non-zero means that there is, in terms of our test, some significant correlation, and we're not claiming either of these. This is just our pair of possibilities. Either there is or there isn't. Once we have that in mind, we can talk about our level of significance. Let me get the right side of my pen out there. Alpha is 5%, where because our alternative is that there is some correlation, not positive or negative, just any, this, like our previous tests, with a strict non-equals inequality, is going to be two-tailed. From there, we need to get our degrees of freedom. In this case, because we are running a correlation test, our degrees of freedom will be given by the formula n-2, where for that data set, we had 10 countries that we're looking at. So we have 10 minus 2, or 8 degrees of freedom. And from there, we need to get our critical values and talk about our rejection region. Where to get our critical values, we have to do something either using the table or the inverse t function in the calculator. Where if we're going to use something like that, because we have two tails, 5%, we're splitting that 5% in each tail, we get 2.5 in each. You can get that one of two ways. I'm going to get the bigger one, 0.975, and 8 degrees of freedom to get that our critical values. So that should probably be more of a colon than equal sign, whatever. Notation doesn't need to be perfect. It's going to end up, but anyway, these are going to end up being about 2.306. So our rejection regions will be t-scores above positive 2.306 and t-scores below negative 2.306, using a bit more exacting notation this time just because. Now if we wanted to, we could also get a p-value here, but the book is going to assume that we don't want that for whatever reason. Who knows? Anyway, once we have this in mind, we can then talk about our test statistic, our t-score, using that formula. So our t-value, in this case, is going to be given by r, 0.874, divided by the square root of 1 minus r squared, so 1 minus 0.874 squared, divided by the degrees of freedom, 10 minus 2, which, plug that all in, and you will get a value of approximately 5.087. Or if you want to think about this in terms of a distribution, you would have a picture like this, where hopefully you can tell just how far off that value of about 5, how far off that t-score, that test statistic is way down in the tail. If you want to get a p-value there, you'd find it's pretty damn small. And accordingly, you can tell that that t-score is in the rejection region. And because our t-score is in the rejection region, as always, even though we have different values, even though we have different pieces, we're still going to end up rejecting the null hypothesis. So, because we are rejecting the null hypothesis, if we want to make some sort of conclusion, make some sort of interpretation, we could say that there is enough evidence for alpha equals 5% to conclude there is significant linear correlation between gross domestic products and carbon dioxide emissions. We can see that based on the information we have, based on the size of our data set, based on the correlation between our data sets, there is a connection. And that connection is significant. It's not just meaningless, random pieces. But, even though it is significant, does that mean an increase in... What was the income? Does that mean an increase in CO2 emissions causes an increase in GDP? Or that an increase in GDP causes an increase in CO2 emissions? Whichever one of those was the X value that I'm now blanking because I've filled my head with too many other things. Maybe, but maybe not. And that's what we'll finish this week with, and this section with, something a bit less formal, a bit less mathematical, discussing the connection, or more importantly, disconnection, between correlation and causation.